All right, so we're looking at 9.3, and this is going to talk about error analysis for series. When we do a series, remember, we're doing a polynomial approximation for some function. Now, you may be wondering, why in the world are we doing this? All the functions that we've done so far are really easy to deal with, but you got to remember, we've talked about in the past that there are a lot of functions that you cannot integrate. And if there's a function that you can't integrate, you can use a Taylor or a Maclaurin polynomial to approximate that thing, and we know that polynomials are very easy to integrate. They're very easy to take the derivative of. There's lots of things we can do as far as once we translate that thing into a polynomial, everything becomes easy. But once you do that, you've introduced some error to your polynomial because it's an approximation. It's not exact. So this is where we're talking about the error analysis for a given series. All right, Taylor series, as we said, are used to estimate the value of functions, at least theoretically. And nowadays we can use a calculator or a computer and calculate to infinitesimal small errors. So we can get it as accurate as we need to with a calculator or a computer, but that used to not be the case. So you need the foundation of where that comes from so you can actually calculate how close you actually are to, what your possible plus or minus might be on your polynomial approximation. An estimate is only useful if we know how accurate it is. If we're doing an estimate that has to be accurate to 10 thousandths, but our polynomial, and we analyze its error and it's off by hundredths, then our estimate is useless for what we're trying to do. When we use part of a Taylor series to estimate the value of a function, the end of the series that we do not use is called the remainder. If we know the size of the remainder, then we know how close our estimate is. For instance, for a geometric series, this is easy. If we use the series 1 plus x squared plus x to the fourth plus x to the sixth to approximate 1 over 1 minus x squared over the interval from -1 to 1, the truncated part of that series is everything that's left. X to the 8th, x to the 10th, x to the 12th, and goes on forever. So the truncation error is the absolute value of the remainder of that thing, which we can actually find by using our infinite sum notation. If you remember, our infinite sum for a geometric series says a sub 1 divided by 1 minus r is going to give us the sum of all those terms. So here our first term is x to the 8th, so there's our first term, and we're increasing or multiplying by x squared each time. So that's where we get 1 minus x squared. And a truncation, we've talked about that a little bit, or I've mentioned it when we talk about 3 decimal places on all your calculator problems for final answers. They accept your answer either truncated or rounded, either one. Truncation is where you just chop the rest of the thing off. So if we had 1.379848, we could chop off everything after that third decimal, and we have truncated that to 3 decimal places. We didn't round, and in some cases your truncation and your rounding are the same value if that next value is less than 5, or the next decimal place, the fourth decimal place is less than 5. But that's the difference in truncation and rounding. Rounding, you actually look at that next place to see whether you're going to go up 1 or you're going to stay the same. where truncation, you don't look at the next decimal at all. You go to 3 decimal places and chop off all the remaining decimal places. Now, of course, this is a trivial example, and like I said, a lot of what we're going to look at are going to be trivial. You're going to look at it and you're going to say, why in the world am I doing this when you could just calculate the actual sum of this geometric series? Well, it's all to introduce the concepts. We're not going to use the concepts necessarily on a problem that's going to be as difficult as you would have to use it in a real situation. But we want to use something that's easy to deal with so you can see, so you can actually see what the rest of this thing is and calculate it, and it gives you a problem that you can actually work, even though we could actually find the sum of the whole thing. Now, Taylor's theorem with remainder says this: if f has derivatives of all orders in an open interval I containing a, then for each positive integer n and for each x in the interval, f of x equals f of a plus f prime of a times x minus a plus f double prime of a over 2 factorial times x minus a quantity squared plus dot 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 all the way through, and then we have anything wherever we stop, the rest is just the remainder. Now, the Lagrange form of the remainder is just the next term. Here, notice we've got f to the nth derivative, the nth derivative of f, evaluated at a over n factorial times x minus a to the nth power. Well, the remainder is nothing more than the rest, the very next term. The Lagrange form of the remainder is just the n plus 1th derivative of f, evaluated at our c, and c we'll talk about in just a little bit, over n plus 1 factorial times x minus a to the n plus 1 power. Now, the remainder after the partial sum s sub n, where c is between a and x. That's what this is. It's the remainder after the partial sum of n terms, where c is some number between a and x. Now, this is also called the remainder of order n, or the error term. Now, note that this looks just like the next term in the series, except for the a, right here, has been replaced by the number c in that n plus 1th derivative. This seems vague since we don't know the value of c, but we can sometimes find a maximum value for that, and when we find the maximum value, that's going to be the maximum error that we can actually entail. Now, if m is the maximum value for f, or the n plus 1th derivative of f, of x on the interval between a and x, then m is going to have to be in between the actual remainder. Sorry, that's not in between. It's going to have to be greater than or equal to this thing right here, which is the remainder, the absolute value of the remainder for the whole series. So this is all those extra terms added up, and we take the absolute value, and it has to be less than or equal to m, that largest value for f to the n plus 1th derivative of f evaluated at x over n plus 1 factorial times the absolute value of x minus a to the n plus 1. So our actual remainder, the absolute value of it, is going to be less than this thing. So if we can calculate this thing, which is what? Well, this is just the next term where we've taken the n plus 1th derivative of f evaluated at some value of x, and we've made it, we've found what is that maximum value of it. And then that is going to be greater than the actual remainder of the series. So if this is our error and it's less than what we need it to be, and it's greater than the actual remainder of the series, then we're within our error that we need to fit in between. And this is called Taylor's inequality. Now, I want you to note that this is not the formula that is in our book. It's from another textbook. But it's an easier way to deal with it. The formula we've got is a little different. All right, so example 2. Prove that the sigma notation from k equals 0 to infinity of negative 1 to the k power of x to the 2k plus 1 over 2k plus 1 factorial, which is the Taylor series for sine x, converges for all real x. All right, so since the maximum value of sine x or any of its derivatives is 1, for all real x, m is going to equal 1. It's the 1 is the largest value that sine x is ever going to be. When we take the derivative, what's going to happen? It's going to be the derivative of sine, which is cosine, the derivative of cosine, which is negative sine, the derivative of negative sine, which is negative cosine, etc., etc. But the maximum value for any of those is positive 1. So here we're going to have a 1 for our m. Therefore, our remainder for n terms, the absolute value of that is going to be less than 1 over n plus 1 factorial times x minus 0 to the n plus 1 power. Now this is nothing more. When we do our subtraction here, we're going to get x to the n plus 1 power, absolute value of it, over n plus 1 factorial. Now if we take the limit of this thing, the factorial is going to grow way faster than any x value to the n plus 1 power. As n gets larger and larger and goes to infinity, the factorial is going to grow way faster than just increasing the power on top. So this is going to go to 0. Well, if that goes to 0, that means that this part goes to 0, which means the remainder is at most, if we keep going for infinity, then the remainder is going to go to 0 as well. Therefore, the series will converge. Now, remember in this limit here, you're thinking of x being a variable. In this limit, x is not a variable. We're just saying x for some value. You know, this is going to, let's say we're doing it for x equals 2. Well, that means we have 2 to the n plus 1 over n plus 1 factorial as n goes to infinity. Now, while we multiply by 2 over and over and over again, the factorial is going to grow way faster than just multiplying by 2 again. Because, I mean, think about this. When we get to where n is 5, n plus 1 factorial is going to be 6 factorial. And then what happens when n goes to 7? Well, up here we're only going to multiply by 2 again. Down here we're now going to have 6 plus 1, which is 7, and we're going to have to multiply the bottom by 7. So the top's being multiplied by 2, bottom's being multiplied by 7, and that's going to, and I mean, those are just small numbers. Expect, you know, kind of think about what's going to happen as n gets larger and larger and larger. We're going to eventually get down here where this is multiplied by 2, this is multiplied by millions or billions. So that's why this goes to 0. Remember, this x for this limit is a set value. Doesn't matter how big that is, we're going to end up at some point with n going to infinity where the bottom is going to grow way faster than the top. All right, so let's find the Lagrange error bound when x minus x squared over 2 is used to approximate the natural log of 1 plus x, and the absolute value of x is less than 0.1. All right, so we're using two terms. So we go ahead and find our series, and we're going through, and we would have this. So f of x equals f of 0 plus f prime of 0 over 1 times x plus f double prime of 0 over 2 factorial times x squared plus our remainder after that second order term. Now, using this as our series, we have f of 0 equals 0 plus x plus negative or minus x squared over 2 plus r2, the remainder of the series. So on the interval from negative 0.1 to 0.1, 2 over 1 plus x to the third decreases. So its maximum value is going to occur at the end, at the left endpoint. So our m is equal to 2 over 1 plus negative 0.1 to the third power. So we do our calculation. And we get that that is approximately 2.714348422,497. Sorry about that. So that's our m value. And notice, remember where this comes from. This comes from our third derivative, evaluated where it's going to have the maximum value. It's going to have the maximum value, as we said here, occurs at the left endpoint of our interval, which is negative 0.1. That's where this comes from. So that's our m value. Don't get confused with the m. All the m is this thing evaluated where in this interval that we're talking about is going to have the largest value. All right, so then we can use Taylor's inequality, plugging our m in here, and our n is going to be 3. So we end up with the absolute value of r sub n of x being less than or equal to 2.27435 times this part right here, at 0 minus the 0.01 absolute value of it to the third power over 3 factorial. So when we calculate that r sub n, our error bound, according to the Lagrange error bound, is 0.000457. So in our estimate of this, of natural log of 1 plus x, the two-term estimate is this close. That's the maximum amount we could be off with just two terms, as long as we stay in the interval where the absolute value of x is less than or equal to 0.1. In other words, negative 0.1 to 0.1. In this interval, we can approximate that to this accuracy. So here we can see if x is 0.1, the actual value of the natural log of 1 plus 0.1 is 0.0953102. If we do this short Taylor approximation of only two terms, x, well actually it's the third term because we had the 0 there, of x minus x squared over 2, we get 0.095. And the error between those two is 0.000310. So we see that that actual error is less than what we calculated it to be. At negative 1, if we calculate all this stuff, or sorry, negative 0.1, we get an actual natural log of 1 plus 0.1 of negative 0.1053605. The Taylor approximation at 0.1, negative 0.1, is negative 0.105, which gives us an error of the remainder of the decimals, 3605, or rounded to 6 decimal places, 0.000361, which once again, less than the error bound we calculated. So this, we are guaranteed that our actual error anywhere in the interval from negative 0.1 to 0.1 is going to be less than this calculation right here. Now, Euler's formula if we were to substitute xi in for x and introduce imaginary numbers into this, we're going to get all this. This is not that important. I just want you to see it. It's kind of interesting. And you will deal with e to the xi, and you'll deal with e to the sine and e to the cosine and all that stuff when you get into more advanced math. So when we simplify, remember all the x squareds, anything that's larger than I to the first power is going to be simplified because I squared is negative 1. I to the third, we can think of that as I squared times I, which is going to give us negative I. I to the fourth, we can think of as 1, and so on and so forth. So when we simplify that, this is what we're going to get, where we have I in some terms, no I in other terms, and we have an alternating series in some ways. Well, it's alternating every two terms. So if we were to factor out the I terms, we get this. Now, what is this right here? What series is that? Well, we have 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. We have all the even numbers over here. Do you remember what series that is? Well, that's your cosine series. And then look at all your the series over here that's multiplied times the I. You've got all the odds. X minus x to the 3rd over 3 factorial plus x to the 5th over 4 factorial plus continuing on. It's going to be all the odds. Remember, what is this series? Well, that series is sine. So we end up with e to the xi being equal to cosine x from this series plus I sine x from this part of the series. So if we let x equal pi, we get e to the I pi is equal to cosine pi plus I sine pi. This is -1, this is 0, so e to the I pi is equal to -1. We can then move that over to the other side, and we get e to the I pi plus 1 equals 0. This amazing identity contains the 5 most famous numbers in mathematics and shows that they're interrelated. They are e, I, pi, 1, and 0. All right, and that's all of this